So you've got this checklist for using formulae. Hopefully you'll eventually get to sort of have this in your head. Quite straightforward really, isn't it? You know, you check it's in the right form. Well, it is in this case. Check units are consistent. Enter the figures, do the calculation, but then think about accuracy and the unit at the end. So we're going to apply that here. We don't have to worry about units because there's only one unit in there that's resistance. So our answer is going to be a resistance. So we can write down what we're actually going to put into the calculator. R1, error. Error in that formula, isn't there? Should be product over sum. Check the formula's in the right form. It's not. RT equals R1 times R2 over R1 plus R2. I did it wrong. Yeah, I wrote it. I copied it down wrong from the formula sheet that we had at the start, which is very easy to do. So beware of that. You know, check you've written the formula down correctly. Check it's right before you use it. So you could say that I've done that deliberately just to make that teaching point.
Why is it wrong?
It should be, yeah. If you look back at the original formula sheet we had, it was R1 times R2 over R1 plus R2. I wrote it the wrong way around. So it should be RT equals 136.58 times 53.6 over 136.58 plus. Yeah. Okay. Yeah. So a word on the use of calculators here. If I'm going to do this on my calculator, I'm going to try and do it all in one hit on the calculator. And that's something I'm going to talk about and we're going to do. The calculator can do this in one go. So don't do that. Write down the answer and then divide it by, work out what the bottom bit is and then divide one by the other. It would work, but you're going to lose accuracy because you're not going to write down the answer, the whole answer probably, to this top bit and the whole answer to the bottom bit. You might round it a bit. And every time you do that, you're losing accuracy. The calculator can do it in one hit. So do it in one hit. If you've got these Casios, you will find on the calculator this button. I don't know whether the bottom or the top bit's shaded, but if there's a fraction button on there. If you hit the fraction button, you can literally, as I was saying, these calculators work very logically. You can literally type in this on the top and then move your cursor down to the bottom of the fraction button and put in the bottom bit and then hit equals and do it all in one go. If you've not got this fraction button, then you've got a potential error. So look up because somebody's going to make this potential mistake. I might be tempted on the calculator to put in 136.58 times 53.6 divided by, because it's over, 136.58 plus 53.6. And if I were to do that on the calculator, I'd get a wrong answer. Can anyone tell me why? Yeah. Yes, that's right. Can we all listen when somebody's, so you don't miss it, please? Okay. Divide by 136.5. What the calculator is going to do is multiply 136.58 by 53.6 and then divide that answer by 136.5. And then it's going to take that answer and add 53.6, which is not what you want to do. You're dead right. You want to divide by all of this. So what would I have to do here to make sure the calculator does this? Brackets, right. I'd have to put a bracket round here. If you use the fraction button on the calculator, you don't have to worry about this. So you don't have to worry about making that mistake. But if you're not using this button, you've got to make sure this is in a bracket, so you divide by the whole thing. So that's a very common error with the calculator. Be careful of that. So you do this, and you get the total resistance, and it turns out to be, someone please, yep, 38 point. Right, so what was it? 38.49 something, yeah? And you've decided to round quite rightly to how many significant figures then?
One.
Say that again? Three significant figures. Not decimal places, significant figures. 1, 2, 3 in here, in this one. 5 in this one, but only 3 in this one. So the rule of thumb, remember, the same accuracy is the least accurate, or maybe one more. You might be tempted to go to 4. So you look at what you get on the calculator, 38.49, well, that lends itself, doesn't it, to 38.5 ohms. And then you quote your significant figures. Always do that if you've rounded it. Okay? Any questions on that? You'll do lots of calculator calculations. We will do some more, and we'll look at some examples of them. And try always to use the power of the calculator and do that calculation in one hit. It will do it for you if you know how to use it. Okay, moving on. I want to just look for a minute at standard form and engineering notation, which we use a lot when we're trying to represent large or small numbers. Here's an example of a relatively large number. We've used it already, 13,600. That's on the sort of borderline as to whether you'd bother to use engineering notation or not. Certainly if this number was much bigger, in other words, if I put another 3 noughts on the end of this, then I would use some sort of notation to represent that big number. The most important one, as far as we're concerned, is engineering notation. That goes in 3s, as we'll see. And that's the only difference between this and standard form. They both use the same idea. What you do is dead straightforward. I'm just going to very quickly explain how it works. If I have a number, you don't really need to make this note unless you really want to. If I have a number like this, for example, going back to that original one, I could easily write that as times 10,000, because if I times 1.36 by 10,000, I actually move the point 4 places, because when you times by 10, you move it once to the right. So that's the same as that. But I can write 10,000 as 10 to the power 4, 10 times 10 times 10 times 10. So I could write that number as 1.36 times 10 to the 4. And if you look at literally the length of this number and the length of this number, as far as writing it down is concerned, not much in it. However, if I want to write a number with lots more zeros on it, it suddenly becomes much more convenient to write it in this form. This is in standard form. In standard form, we move the decimal point to the right-hand side of the first significant figure, always in standard form, which is here. So we move it to the right-hand side of the first significant figure, that one. So it goes there. And then we just count how many times we've had to move it. 1, 2, 3, 4. So then we put times 10 to the 4. Bingo. Done. Okay? In engineering notation, we go in 3s. So that's not in engineering notation because it's times 10 to the 4. So what I'd do is I'd say 13.6 times 10 to the 3, because now I'd have to only move it back 3 places. and that would be in engineering notation. And remember, that's what we're sticking to. So, engineering notation. Because that lends itself perfectly to prefixes like kilo and mega, which go in threes. So engineering notation is the same idea as standard form, but only goes in threes. So, no, yeah. No, you could have many significant figures. Your decimal point always goes to the first significant figure in standard form or to some convenient multiple of 3. Yeah, is that answer your question? It doesn't necessarily have to be 3 significant figures, no. For example, that's only 2 significant figures. So I put the commas in. It's quite a big number. 1.2 billion or 1,200 million. Okay. If I wanted to write that in standard form, what would I write? How many times have I got to move the point? Remember, if there's no decimal point, it's always at the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it so happens I'll pick one where standard form and engineering notation would be the same. Okay. Is that correct? It could be, yeah. Yes, that's right. That 2 is in engineering notation. I might well want it like that. 10 to the 6, as we're going to write down, is the prefix that we would call what? 10 to the 6, a million, is mega. So that would be a mega, whatever we're talking about. This would be, what's 10 to the 9? No, not tera, that's 12, giga. So that would be giga, this would be mega. We'll write these things down. So you might want it to be in mega joules or mega something. You might want it to be in giga. So there's no right or wrong answer to this in engineering notation, but in standard form, it would have to be this one because it's got to go after the first significant figure. We don't use standard form so much, we tend to stick to engineering notation. So back to this again. What would this be in standard form? Times 10 to the 7. Yeah, if you count back, I've had to go 7 places. 1, 2, 3, 4, 5, 6, 7. What would it be in engineering notation? 13.6 times 10 to the 6. Yeah. Or right, I could go 13,600 times 10 to the 3. Yeah, that means I've just got to go 3 places. So going from there, 1, 2, 3, and I'm back where it should be. Yeah, either is correct. Again, it depends on what you want it to be, how you want it to be left. So there's no answer to that. There's no right or wrong. It's just whatever units you want. Yeah, you could use all 3. This is standard form. Yeah, yes. This is engineering notation, and so is this. Okay. You will come across them. Yeah. All right. We also, as we'll talk about, need to represent very small numbers. We'll come on to that. That's almost exactly the same. But before we leave this, I want to look at an example and think about how we put this to a calculator. So, everybody happy that they've made the note they want? Moving on. I want to do that multiplication, but I want to do it on the calculator. Before I do it on the calculator, I want to estimate it. Estimation is useful, especially when you're using engineering notation or standard form, because these times 10 to the, and you can get really big and small numbers. So it's difficult to have a feel for whether or not the answer is right or not when you've done the calculation. So again, some people do this, some people don't. It's a good skill to cultivate. Let's try and estimate this. I'll show you what I would do to estimate this. First of all, I round the number to one significant figure. I'm only estimating it, so I'm only interested in first significant figure. That's 1 to one significant figure. This is 3 to one significant figure. 1 times 3 is 3. So that's my estimate for the number. It's about 3. This, as we'll learn from the maths of laws of indices, powers, when you're multiplying powers, you add them. So 4 plus 8 is 12. So add the powers, 4 and 8 is 12, and then just round the numbers to one significant figure. That gives me an estimate of about 3 times 10 to the 12. So I've done that in my head. That means now I go to the calculator and I've got an idea what it's going to be. So if it's not around there, I'm going to do that calculation again on the calculator because I might have made a mistake. Now I want to do that calculation on your calculator. So if you've got your calculator here, have a go at it. Elise, isn't it? Elise, is that right? Can I borrow that calculator that you borrowed off me a second? Can you bring it up here? Oh, it's all right. I've got this one. Right. Look at your calculator. At the bottom, you've got a times 10 to the x button. Does anyone's calculator not say times 10 to? It might say EXP or something. You've got an old one. What does yours say? Sorry, name? Brian. What does yours say? Does it say? Yeah, so that's the same as this. Okay. You might find that it's worth investing in a more up-to-date one of these because you might, all to help you with your maths. You know, every little helps, doesn't it? So get a more up-to-date one. Did you?
Yeah, well, that's one of the best calculators you can get.
So to put it into the calculator, 1.36, don't key in times, don't press the times button and then 10 for 10. That button, the times 10 to the x button, does that bit. So the times 10 to the is on a button. You don't hit times 10. You just hit that button and then hit the number 4. So 1.36 times 10 to the 4. And now you hit multiply, and then you put the number in. 3.2 times 10 to the 8. And then equals. And what do you get? 4 times 10 to the 12. And so now I say to myself, yeah, my estimate, so that looks right because you got times 10 to the 12, so I believe that answer. Okay. Appropriate accuracy, Cameron, is it? Is it Cameron? Ross, is it appropriate accuracy considering the numbers you put in? Go on. 4.35. Why 5 and not 6? Yeah. 4.35 times 10 to the 12 to 3 significant figures. Yeah. Always put that on if you're rounding, otherwise somebody might think that's an exact answer from the calculator, which it isn't. Okay. I'll just pause. Try that. Remember the little estimation skill? What did I do when I multiplied numbers together to the powers? Sorry? Yeah, when I multiply, you add the powers. So when you divide, you take away the powers. So do an estimate. Round each one to one significant figure. And we'll go through it together, but estimate your answer and then try it on the calculator and see what the answer actually is to an appropriate accuracy. Estimation, what would you do? So what's 4.3 divided by 2, which is just 2, isn't it? Times 10 to the 5. 8 take away 3 is 5. So it shouldn't be a calculation you need to do on paper. It should be in your head, you know, a quick estimate. So anything times 10 to the 5 is going to look reasonable. And when you do it, you get... And have you rounded that, Cameron?
Yeah.
So what do you put at the end?
No, around 226,315.785.
226,000, sorry, go again.
315.785.
Right, okay. Yeah, that's what the calculators, some calculators, is that what people are getting, that sort of thing? So, first job, move it to standard form or some sort of engineering notation. So I'm going to go back 1, 2, 3, 4, 5, 2.26315789 times 10 to the 5. But of course the accuracy is far too great, isn't it, for the calculators doing all that. I can only really give it to 2 significant figures, so 2.3 times 10 to the 5 would be fine. In engineering notation, what would you do? Got a choice. I could either go left or right. Sorry? Yes. Remember that 5 means I've got to go 5 places to the right. So if I shift it one more place to the left, I've now turned it into engineering notation. I could have gone the other way a couple of places and called it 230 times 10 to the 3. And again, there's no right or wrong answer there. Yeah? Yes? Yeah. No, I haven't, afraid. Both of mine are out on loan at the moment. You just have to share with someone. Okay. Right. Now, make a note of this exercise 19, page 37. I know you've not got the textbook yet. That's what I want to look at. So I'm going to put it up on the board for now because I've got an electronic copy. So I'll put that up for us and we'll all have a look at some questions now. Exercise 19, page 37. Let's have a look at this then. So this is a good general introduction to all the exercises. They're all the same sort of idea. You get a question and in square brackets at the end is the answer. So you can, once you've done the calculation, you can see whether you got it right or not straight away. Okay. So some people are a bit disappointed to see the answer there, but I don't think it ever matters because you've still got to do the calculation to get there. So to me, it doesn't matter. So let's look at the way they work. A formula used in connection with gases is R equals PV divided by T. So that slash there means divided by. PV in brackets, not really necessary to have the bracket there, but the formula is to get R, I multiply P by V and then divide by T. Evaluate R when P equals 1,500, V equals 5 and T equals 200. So you just plug in the numbers, as we've been doing, use the formula, get the answer. Here's another one. The velocity of a body is given by this formula. V equals U plus AT. Some of you might recognize that formula. The initial velocity U is measured when time t is 15 seconds and found to be 12 meters per second. If the acceleration A is that, calculate the final velocity V. So one thing you have to do with these things, and we were talking a minute ago about the use of maths? Well, part of that is extracting information from a problem. So you've got a problem here. It might be a problem at work. You've got to take from that the essential information and do something with it. You're given a formula. It doesn't say U equals A equals T equals, but somewhere in the rest of this question is the information. So you extract the information and then plug in the numbers. I'd be very surprised if in this one, these two, for example, there's no problems with consistency of units, so that's fine. If we move on and look at, carry on down a bit, it'll let me. Oh, no, I've done it. Here we are. No, it's exercise 18. Do you think they know we're here? We get to number 4. Suddenly comes in standard form. 5 times 10 to the minus 6. Minus is for very small numbers, so key it in exactly the same way. 5 times 10 to the minus 6. Number 5. Yeah, you're okay. And so on. I know 1 or 2 of them in here, you've got to be a bit careful of units, consistency of units. So what I want to do now, it's 11 o'clock, we finish at 11:30. I want 5 or 10 minutes at the end to talk about the assignment 3, the statistics. So 20 minutes, I'm going to leave them up there, working together. I want you to have a go at some of these questions. Okay?
The assignment like been set now.
The assignment you get when you've done these recommended questions that I'm going to show you now. Oh no, insert blank page. Okay, so I've already showed you roughly where they are on the internet. Let's go back to it. If you go to, those links I gave you, if any computer in the college, so if you've got some time today, you could go there. Go to the BTEC one that I gave you. And then go to the Unit 4 tab on there, the Maths tab. You get this that I showed you. Assignment 3 is what you're interested in. So if you click on the Assignment 3 link, because that's the first assignment you're going to be given, they're not given out in the order that you might expect. These are the files that are going to help you down at the bottom there. So there's no video clips or anything at the moment. But that's the one I've just put on. That's chapter 37 from the textbook that you're buying. So until you've got hold of that book, you can have a look at this. Okay? The exercises and required questions, that the one that I asked you to give back to me because I hadn't got many left, is this one. So these are the 2 that you're interested in. Next week we're going to be talking about histograms and stuff like that, but there's a PowerPoint presentation there that I'll be using then. So if you want to have a pre-look at that, by all means. So there's a PowerPoint presentation on histograms. There's a chapter for you to read that includes histograms and also these cumulative frequency curves, as well as pie charts, bar charts, and all the other stuff that I'm hoping you're familiar with, although maybe a long while ago. So these are the exercises that are available, and the required questions are on there. So if I just quickly fire this up, you'll see I've just put in a series of slides these pages. So you might find you've got to zoom in on them. I think the PDF file allows you to do that so that you can read it. You can zoom in on the page, look, and read it. Looks a bit blurry, or is it just my eyes? But anyway, there is the information. So you can scan through that, and at the end of it are the exercises. Okay? So that I'd like to have a look at for next week. I want you to get your book on order, and then I want you to have a look at that so you get familiar with the sites. Okay? One more thing to do just before we pack up. I can tell you, desperate to go. Review. Right. Back row. Tell me something that you've learnt today. Anyone off the back row? Don't pack up, please, for a minute. Formulas. What? Any particular one? Remember a formula. Which one? What is it? The formula. Resistance total equals. Well done. That formula, yep, okay. So you, and actually part of the drills, eventually I'm going to be asking you to remember some formulae, and that's maybe not one of them, but some I will. Middle, something you learnt today, anyone on the middle bench, different to that? Engineering notation, sorry? Right, goes in threes, yeah. Correct, that's right. Which fits in with prefixes, and more on that next time. Front bench. So what about units, Daniel? No? Units. What is important to remember about units? Anyone on the front bench? Got to be consistent, yeah. Are we all happy what that means?
Yes.
Yeah. Okay. Thank you for your attention, and I will see you next week.